Hi everyone, welcome back. Let's go ahead and finish up our ratio test notes. Two more examples. Example 4 says find the radius of convergence of this series. So starting at 0, going to infinity again, of the quantity nx, or n times x to the nth power. Okay, so we're going to set this up the same way we did the last few. So L is going to be the limit as n approaches infinity. I hope you've copied and pasted that part by now because it's going to come up quite a bit. Okay, so what is the a sub n plus 1 term going to be? So again, just like last time, right, we need to replace both of these n's with the quantity n plus 1. So this is going to look a little goofy. So I went with square brackets, right, and then parentheses n plus 1 times x, and then this whole thing in the square brackets is going to be to the n plus 1 power. Okay, so both of the n's are replaced with n plus 1. And then my denominator is just the general term. So this is quantity nx to the nth power. Okay, and now the good news here is that we have these brackets or the parentheses, right? So everything in the brackets can get this exponent. Same thing with these parentheses down here. They can get their own exponent as well. So I'm going to rewrite this limit as n approaches infinity of, I'm going to write n plus 1 to the n plus 1 power times x, which is also going to be to the n plus 1 power. And my denominator is going to be n to the nth power times x to the nth power. Okay, and now, again, this one looks very odd, okay, but we can combine some stuff here, right? I have these two x terms. I can subtract the exponents there. And what I'm also going to do is I'm going to take this n plus 1 to the n plus 1 power, and I'm going to break that up, right? So this n plus 1 power, right, means I had an n plus 1 to the nth power times an n plus 1 to the first power. And my denominator I'll leave as n to the n still. And now x to the n plus 1 over x to the n, right? That's just going to give me an x or an x to the first. If you want to write the 1 with the exponent there as well, it can't hurt. Okay. And now, just like with the last couple of questions, right? X term does not get affected by this limit. We're going to treat it as a constant. And so I'm going to write absolute value of x on the outside. And now this is going to be a limit as n approaches infinity of, or absolute value of, and now I have two terms that are to the nth power, right? I have the n plus 1 to the n, and I have this n to the n. And so I'm going to kind of group those together, and I'm going to write n plus 1 over n all to the nth power. And then I have an extra n plus 1. Okay, so what does this limit equal? Okay, so this looks pretty goofy here. All right, this looks pretty crazy, okay? But really, the thing that we want to focus on with this limit is actually the n plus 1, right? That's separate over here on the right. Because n plus 1 over n, as n goes to infinity, this is basically just going to be 1. Right? So 1 to the infinity, this is just going to be 1. We're not really going to worry about this, right? But as n goes to infinity, this is going to keep on getting bigger and bigger and bigger, okay? So this brings up something we have not seen in the other examples, right? This limit is infinite, okay? So what do we do about this, right? What do we do here, okay? And this is where the x comes into play, right? So the only way, right, we can guarantee that this is going to be less than 1 is if x is equal to, it has to be 0, okay? The only way to get this to work, right? The only way to get L to be less than 1 is to make x equal to 0, because now 0 times anything is just 0, right? And so we can turn L into 0 if x is 0. But if x is any other value, this limit is going to go to infinity, and so any x value times that is just going to be infinite. And we'll say for x not equal to 0. Okay? So here's what's going on, right? The bottom line here is that this series is only going to converge when x is equal to 0. Okay? This will converge when x is 0. At any other x value, it is going to diverge. And so what that means is, in terms of a radius of convergence, if there's only one point, right, x is equal to 0, that makes the radius 0. How about an interval of convergence? Well, x can be 0 at the minimum, x can be 0 at the maximum, right? That's a goofy looking interval of convergence. Okay, but those are our answers. All right, so that's kind of a weird question, okay, right? But if you have an infinite limit there, right, your only option is to try to make your x terms, right, equal to 0 somehow, okay? So that was example 4, okay? Let's go ahead and take a look at our very last example, all right? Example 5 asks us to consider this series, n is equal to 0 going to infinity, right? Summation of the quantity natural log of x to the n. Okay. So what's going on here? Okay, so ratio test, L is going to equal limit as n approaches infinity, right? So this is going to be the natural log of x, to the n plus 1 power. Again, all of this is in absolute values. I know I don't always say that, but it's always there, okay? And then the denominator is just the natural log of x to the nth power. Okay, and now, good news, same base. I can subtract the exponents. And so this is a limit as n approaches infinity of just the natural log of x. Technically, it's all to the first power, right? But I don't need to put it in parentheses and say first power, okay? And again, like many times before now, this does not have any n's in it, right? And so we can take it out and treat it like a constant. And so this limit becomes the absolute value of the natural log of x, okay? And that is my value for L, all right? Natural log of x inside absolute value, and really, you know what? Sorry, let me backtrack. I was going to say something and I realized it was wrong. Okay, so let's go back now, right, and treat this like example 1. Okay, so my L value has an x here, so I want this L value to be less than 1. So absolute value of natural log of x has to be less than 1, right? But unlike with other questions, in order to figure out the radius, we can't really stop here, right? Because when it's x minus 7, right, you know, you're adding 7 to both sides, right? So it doesn't really affect the radius, right? But the natural log here makes things a little bit goofy, okay? So we cannot stop here. We have to get this x by itself, okay? So let's go ahead and do that. So I'm going to get rid of the absolute value, make it a compound inequality, -1 less than natural log of x less than 1. How can I get rid of a natural log? Let's take everything with a base of e, right? So this will be e to the -1st. E to the ln of x is just x, and then I get e to the 1st. Okay, and so e to the -1st is just 1 over e is less than x is less than e. And that would be my interval of convergence. Okay. And now, unlike a nice answer with some, integer values, right? We can just subtract and divide by 2. We can still do the same here. We just can't really simplify it, right? The radius of convergence is just going to be your range. So E minus 1 over E cut in half. Okay, that is going to be the radius of convergence. Okay, and now part B says, to what does this series converge, right? Well, if we take a look at the series itself, natural log of x to the n, right? So if I start plugging in values of n, right, anything to the 0 is 1. My next term would be natural log of x. My next term would be the quantity natural log of x to the second power, and it would go on and on. And so could have helped us in the beginning, right? This is a geometric series. Every term is getting multiplied by the natural log of x. Okay, and so we can go back to the first page, right, and use our formula, right? We know that r is the natural log of x, and so sum of an infinite geometric series, a sub 1 is 1 over 1 minus my r value, which is natural log of x. And that's our answer there. Okay. All right. Good work, everyone. And I will see you next time.